Yeah, hello. Good morning, good afternoon, and good evening, everyone. I would like to first welcome you to the second season of the Young Researchers Forum on Detonation. And this is our first presentation for the new year. I would like to introduce today's speaker, Dr. Minh Luong. He obtained his bachelor degree from Hanoi University of Science and Technology in Vietnam. He then pursued his master and PhD degree from Ulsan National Institute of Science and Technology in Korea in the field of direct and numerical simulations of advanced combustion concepts. Since September 2017, he has been a postdoctoral fellow in Professor Yim's computational reacting flow laboratory. Currently, his focus is on understanding the mechanisms of pre-ignition, deflagration, and detonation in combustion devices such as internal combustion engines, shock tubes, and the rapid compression machines. Partially, he also contributes to developing KAUST adaptive reacting flow solvers to prepare the next generation of high fidelity and high performance DNS in exascale era to fully utilize the heterogeneous architecture of supercomputers. Right? And I would like to give the podium to Dr. Luong. He can feel free to start his presentation. Yeah, I will stop sharing here. Yeah, please go ahead, Minh.
Yeah, thank you very much. Could you see my screen?
Yeah, you can see.
You can hear me very well, right?
Yeah.
Okay. Thank you very much for organizer of this forum that allow me to share my work here. I welcome for any question and suggestion to improve my study. Hello everyone. My name is Minh, a postdoc in Professor Hồng Yim Group. The topic of my presentation today is about the engine knock with temperature inhomogeneity. So the main phenomena here is from end gas autoignition to detonations. And how can we predict and prevent these phenomena? First, I would like to thank KAUST for financial support and KSL for providing computational resources. And also here is a co-author contribute to my work. For who are interested in our study, and here are the three relevant studies that directly relate to my presentation. You can find my study, recent study from Google Scholar, all of this publication. And here's the outline of my presentation. I will walk you through the introduction of abnormal combustion process, normally referred to pre-ignition and knocking issues in combustion device. And after that is theoretical background, and we will try to develop a model to predict the engine knock, and we will validate it by using direct numerical simulations. And for those who are not familiar with some terminology, and here is some key terminologies I refer to. First is the ignition delay time. When you burn a fresh gas, it will this is not burn, it will auto-ignite, and after a duration, people refer it to ignition delay time from starting to the peak of the heat release rate. This is referred to ignition delay time. And there are very short periods where the mode of the heat release occur from 5% of maximum heat release to the peak. This is referred to excitation time. And in the combustion, normally, if the combustion process is dominated by deflagrations, it is kind of flame-like front, low speed here, you can see here. It is called deflagration. However, when you have spontaneous autoignition, it's like a volumetric ignitions. You will have very rapid heat release rate here, the peak is much higher than the case with slow speed deflagration, and we call this one a deflagration, the blue curve, and the rest one is for spontaneous ignition. There are an extreme case where we have detonations. It will call is a supernova in the engines. This event is characterized by extremely high pressurized, normally around 200 to 500 bar, and the speed around 2000 meters per second. It normally close to the Chapman-Zugast and von Neumann conditions. And I will refer to this diagram later in my talk. So let's get started with the introduction of the combustion process in the combustion device. First, let's get started with the internal combustion engines. Downsized and boosted internal combustion engines can provide high thermal efficiency and no emissions. However, at high load conditions, the engines are more prone to pre-ignition, knock, and supernova. It refers to also detonation. And you can see from the animation here, we have a very early phase of deflagration, slow speed, and then it evolves into the detonation front. In this animation, you can see clearly the iso contour of the pressure at the CJ state, around 200 bar, and when it takes place, it will consume the rest of the mixture instantly. In this simulation, I slow down this process so you can see clearly. And whenever the supernova occur, you can see it will induce very high amplitude of the pressure wave, and because of the high pressure wave, a few hundred bar, it can damage the combustion component like this one. And there are other circles. Normally it's just end-gas alternation, it just generates a locking, and normally this one is not dangerous like a supernova event. The pre-ignition and supernova is not only occur in the internal combustion engines, it also occur in the RCM. In this very interesting study, the author already tried to investigate how the pre-ignition can induce the detonation. So what it does is they try to initiate a pre-ignition by an ignition source, and it will evolve into flame, and it heat up the mixture. Deflagration, you can see the process from left to right. The deflagration will evolve, and then there are some, when the mixture is burned and propagate, it will send the acoustic wave to the whole chamber. And finally, when the mixture is ripe for the alternation, it evolves, and from alternation to detonation. And we can see here, they capture the process from the alternation to detonation, and it just consumes the rest of mixture. And when it occurs, you can see very high spike of the pressure rise rate. Another phenomena people also observe in the shock tube, they also observe different combustion phenomena. Normally, ideally, in the shock tube, they try to monitor the ignition delay time, like you see in the solid line here. So what they want is the ignition should be homogeneous. At it, you can see the fourth row here, everything is burned simultaneously. However, when the reactivity of the mixture become increased, and especially for the case with cool flame like N-hexane, the mixture become very reactive, and for the long testing periods, you can see there are some ignition kernel. It developed into deflagration and evolving, and finally the end-gas alternation happen. When the phenomena occur, you can see the ignition delay measurement, the simple in this figure, is much shorter than the theoretical ignition delay from the model. So there are big gap between the model and the measurement. So this kind of experiment result here is the usefulness, because there are a big difference between the measurement and the theoretical. So the experiment is usefulness, so we want to avoid this one. I not go into detail in this study. We working on this one, and we develop a criterion to characterize strong ignition, intermediate, and weak ignition, and we will publish this work soon in this year. And here is just the animation from the figure I show you. You have a very early pre-ignition, develop into flame, and then compress the mixture, and finally auto-ignition. And sometimes end gas, if the mixture is so reactive, it can develop into the detonation as well. And detonation also is studied in a closed chamber with very high turbulent intensity. This work is published recently in this group. What they try to do is they initiate a flame with very high turbulent intensity in the left hand side here, and in the right hand side it is closed chamber. And you can see for this mixture it's not so high reactive. After two reflection at the end wall, the detonation will involve from the end wall, and it develop into detonation. In this case, they use a hydrogen airfield. In another scenario, they try to increase the oxygen concentration. It means that the mixture will become more reactive, and we don't need two shockwave reflection at the end wall like this case. In this case, it just developed immediately on the way it reached, before it reached the end wall. So because of when the mixture is so reactive, it's very prone to go to detonation. And we also put our effort to simulate the supernova under the IC engine condition. And here's the animation from this our study, recent study. It shows that the process is go from deflagration, and when the mixture is so reactive, like a very high temperature, we try to simulate the end gas alternation, and it can also develop into detonation. But it requires a running distance long enough. If it's short, it's just alternation. If we take some snapshot from 2D or 3D, we can see that the structure of the detonation is quite complex. In this context, you can see the complex interplay between the alternation front here, and there are some interaction, and it will induce some detonation wave here. And in this context of multi-dimensional, we try to formulate a predictive model to predict this phenomena. And here's the motivation of our work. First is develop a model, try to predict supernova and the knock intensity for multi-D problem. And we will use a 2D and 3D direct numerical simulation, and we analyze the data to validate the prediction. And in this case, we will use ethanol for this study. At the end of my presentation, I will also show some case with DME. There are some cool flame, and I will talk about that one by one. And first, let's go through the theoretical background on the engine knock. Normally, it refers to the alternation of reactant mixture with some level of inhomogeneity. So here we just pick up only the temperature inhomogeneity, but in the engine you can have a composition inhomogeneities as well. And the needling work is by Zerovitz work very early in 1970 something. And also based on his work and other people work, Bradley already built an ignition regime diagram, as we can see here. But this one is a one-dimensional regime diagram. What it means only is normally to build this ignition regime diagram, we will have a linear temperature profile, a slope with certain level of slope, and we will try to compute the two non-dimensional parameter. Here is C and epsilon, and the parameter will be computed at the middle of the hotspot. And when these two parameters fall within this regime is bounded by the upper C and lower C with certain level of specific value of the epsilon, we will have a detonation development regime. If we go up upper branch, it will be deflagration dominant, or if we go to the left here, it also can be very small hotspot that cannot bring the system to detonation. So the theoretical background here is mainly come from the gradient of the ignition DNA. For a given slope of the temperature here, we can compute the gradient of ignition DNA, and we can estimate how fast the reaction front can propagate. When when the mixture is auto-ignite, it will have some relaxation. Mixture will be expanded, and we will have the pressure wave. And pressure wave normally is proportional with square root of temperature. Within this developing detonation regime, where the speed of the reaction front and the acoustic wave is coupling, I just try to sketch here. The speed is comparable. The mixture will ignite and can evolve into the detonations. And this one it refers to this case where the pressure can go up very high, a few hundred bar. Other than that, if we go upper this level where the speed of the ignition front is very slow, the acoustic wave that leaves the ignition front quickly, and there are no coupling, we will have a upper limit. For the lower limit, the C lower value here, where the reaction front is so fast, it will much faster than acoustic wave, and it just escape, and there are no coupling, and we also have no detonation. So there are to summarize, we need have two parameters, C and epsilon, and within this regime we will have detonation development. So I will demonstrate by some 1D animation. For this case, I have very small hotspot here, very small hotspot. So you can expect that the detonation will not develop for this case. You can see the hotspots that involve into the flame, and the rest of the mixture will be consumed first by deflagration, and when the mixture is become reactive here, it reaches the ignition point, it's at auto-ignite, and there are no coupling. And you can see the level of here is the level of pressure is at around 100 bar, and this is at equilibrium pressure. However, in this case, I try to increase the hotspot size become bigger. In this case, the hotspot size around 5 millimeter. You can see that the detonation can evolve immediately. There are perfect coupling between the ignition front and the pressure wave. You can see here, slow motion. You can see it immediately from the detonation front, where the pressure is around 350 bar, and it just consumes the rest of the mixture. So this one is a kind of refer to direct detonation development. If you have a right gradient level and in a big hotspot size. And the last scenario is deflagration to detonation transitions. First, we similar to previous case, we also have a slope of the temperature gradient. And in this case, I just reduce the mean temperature from 1200 K like before to the 100,000 Kelvin. So the ignition process will go through two processes. First, it alternates, but it decouple. And you can see the pressure way here, it leaves the ignition front. And here is a flame. You can see there are no coupling. However, after a few times of reflection, the deflagrations keep propagate on the right, and the mixture become more reactive here because of the heating of the flame here, and also the ignition delay becomes shorter and shorter. Finally, you can see there are, you can see here at this moment, you can see the detonation front start to establish, and it will consume the rest of the mixture. You can see this time the pressure, the maximum pressure can be a few 400, more than 400 bar. And it just consumes the rest of the mixture, you can see. So this one is referred to deflagration to detonation transitions. Previous, I just demonstrated some 1D simulation. It is to reproduce the Bradley diagram. How can we extend 1D model for multi-D problem? And we try to use a scaling analysis and computational diagnostic from DNS data to predict engine knock. And here is summary of the predictive epsilon criterion under the constant volume conditions. What it does here is the predictive criterion will try to reproduce the epsilon in the Bradley diagram. We also have length scale. We have a south speed and exothermicity time scale here. So first, let's talk about the dissipation element here. If you have forgiven initial temperature field here, this is temperature field. If we decompose it, we can decompose into the dissipation element. What it does is the dissipation element is the length scale in which the length over which the temperature variation is monatomic. You can see I just get it here. It will go from high temperature to lower temperature, and this one is monatomic, and then another dissipation element, and here another. If we compute all of this dissipation element and we take the average, basically we can approximate it by the Taylor length scale, the scaling here. And so by using the dissipation element, we can decompose the temperature field into the small length scale, and we can approximate it by Taylor length scale. And another parameter here is the exothermicity time scale. And we put all the parameter here, and then with some scaling we can compute it epsilon p. In this study, at the length scale equal to 3.3 millimeter, I will mention about what does mean in this length scale. We will expect that there are transition between detonation to alternation. If it less than 3.3, it's an alternation dominant. If it's greater than 3.3, it will be detonation development. And here is how can we determine the exothermicity. I think for the detonation community, it's very clear. But for those who are not familiar with this one, I just walk you through this one briefly. When we use a ZND model, we will assume we will compress the mixture from the fresh gas immediately to the von Neumann condition by a shock wave with the speed of the CJ speed. And because the process is so fast, there are no reaction happen. And we push it, and the mixture will take some time for the reaction to occur. And this is a process where the reaction start to take place. And if we monitor the time period when the mode of the exothermicity occur here, this one is referred to the exothermicity time scale, and we will use this value to compute the epsilon p I mentioned before. And here is the initial condition from my 2D and 3D DNS. I try to mimic the N gas auto-ignition, so I choose the condition of 1200 Kelvin, and also to save the computational resource, make the ignition delay short. The parameter I try to play with here is I keep fix the initial pressure and sorry, this one should be stoichiometric meter. This one is V equal to 1. What I change here is I will change the level of fluctuation in the temperature field. So I will change the temperature root mean square. Sometimes people call it standard derivation. The T prime is ranging from 15 Kelvin to 0.5. I change this parameter to make the gradient of the mixture will change, and also to study the turbulent effect. We also change the velocity of the mixture from various from 16 to 80 something. And another, there are two length scale we also change here, is the length scale of the temperature field. We refer it is the most energetic length scale. It's at the peak of the energy spectrum here. We refer this one to LT. And there are two length scale here. We have temperature field like this one, and also have another random turbulent field, and it's called LT for turbulent, and LT here is for temperature. And we will play with parameter from 1 to 10, for velocity from 5 to 1, because we target for the parameter to make sure we will go from no detonation to detonation. As I mentioned before, we have predictive criterion epsilon p, and I compute it at the small length scale of temperature field 1 millimeter, even for 2 millimeter, with the level of fluctuation is 15 Kelvin. This level of fluctuation usually observed in the engines. You can see that for this predictive condition, it's just less than 1. So we predict that the mixture is just go for auto-ignition dominant, no detonation development. So you can see from this animation, you can see that the mixture will auto-ignite into deflagration, and there are N-gas auto-ignition. The pressure here is small. It's close to the equilibrium pressure of the mixture. So we test for two cases, the length scale from 1 to 2, and we confirm that there are no detonation development for this case. We also try to vary the T prime for this two length scale. I mentioned before, from 20 to 2, and we don't observe any case for detonation development. It means this mixture have a length scale running distance is very small. It cannot support for detonation to involve into the detonation. You can see when the auto-ignition happen, most of the mixture already consumed. However, in this another scenario, we try to increase the length scale from 1 to 5. This case, we estimate the epsilon p equal to 1.4. It means it greater than 1. We expect that the mixture will go for detonations. And by do some analysis, we know that at this condition, the level of temperature fluctuation can bring suitable C parameter for mixture to go to detonation as well. So you can see there are first the mixture will auto-ignite and involve into deflagration. It sends out some, you can see there are some acoustic wave generation. And then you can see there are two auto-ignition kernel interact, you can see. And it involve into some detonation front. And when it becomes a stable detonation front, it will consume the rest as a mixture quickly. In simulation, I just slow down the process so you can see the Let's watch one more time. You can see deflagration, interaction, and finally we can see detonation wave propagate and consume the mixture. And in this case, when the detonation happens, the peak of the pressure is around 300 to 400 bar. We also try to do 3D to compare with 2D, and similar observation also observed for the K with length scale equal to 5 millimeter. The comparison between 3D and 2D quantitatively gives the same expectations. Have a strong detonation process. You can see there are wave interaction, and it forms the detonation front. The blue isosurface here is a CJ state, and it involved into detonation. To summarize previous animation, here is a quantitative comparison between different cases. Here is a figure here shows the temporal evolution of the maximum pressure we monitor spatially in the domain and in time. When we increase the length scale from 1 to 5, and we can observe that the epsilon p parameter here go from 0.3 to 1.4. For very small length scale here, the maximum pressure is close to the, you can see the red curve here, is close to the equilibrium pressure, so it's an alternation dominant. However, when we increase the length scale up to 5, we move the mixture, this bigger length scale allow for longer running distance, and we can see the detonation start to develop, and it consumes the mixture. It can maintain the level of very high peak of the pressure here. And if you can note from here is the maximum pressure even higher than the von Neumann condition because of shock interaction. So here is a 1D result, and if you look at the temporal evolution, you can see here for the fourth row is a very small length scale, so we don't see very small length scale, so there are no room for detonation development. However, for this one, when the length scale become bigger and bigger, detonation front can establish very stable detonation front at the end. And next, we try to do some analysis to predict the knock intensity from the initial conditions. So first, if we perform 1D simulations with a lot of the hotspot size and level of gradient, we can reproduce the Bradley diagram. So you can see here with a certain level of the C parameter, approximate go from 1 to 10. We can see the pressure, the maximum pressure go up very high. And this one is a location where the pressure above the equilibrium one. So what does it mean when we do DNS analysis? We learn from this one is for given initial conditions, we can compute the spatial distribution of the C parameter. And when we can compute the C parameter, we can do the PDF. And if the mixture, if we take the mixture with C parameter from 1 to 10, we call it one fraction, FD. It will account for the detonation development. And of course, we need to have a certain parameter of the epsilon P to make sure that we have enough running distance for detonation development. So there are two components. One is a fraction of the C parameter and epsilon P. How can we validate this FD parameter? In DNS, we have the heat rate, net emission at each grid size. We know the no-core pressure, and if the no-core pressure is greater than the equilibrium pressure, we will account this one for, we call this one is FH. This basically is a fraction of heat rate above the equilibrium, and we expect that the FH and FD is comparable, and this is a metric we try to validate, compare with FD with FH. And here's a summary of all of the DNS we run by varying the level of gradient fluctuation and also the length scale. We can compute the FD from initial condition and FH from DNS. The perfect correlation will be zip night. Basically, if we go up like this one, the length scale will increase. The likelihood of super log will be developed. When we decrease the length scale here, low log happen. And when we have very length scale, big length scale from 5 to 10, we will have a detonation development. And the correlation between FH and FD agree very well. So it means the predictive knock intensity characterized by FD is predict quite well with when compared with FH. This is about this figure. Let's look at this right hand side figure. From the 2D initial condition or 3D, we can compute the mean C parameter, and we also plot with its correlation with FH and FD. You can see just for certain level of mean C, where the fraction is high, we will have a very strong detonation occur within this location. So basically, the mean C will go from 1 around from 20, where the strong detonation will happen. If we go beyond this location, right hand side or left hand side here, there are no detonation developed. So if we can determine, if we can model the mean C parameter here, we can predict some level of FD or FH by this correlation. So I will not go into detail about this mean quantity here. Next is the effect of turbulence. The effect of the turbulence on the log intensity. So from previous simulations, we know that with small length scale, we have no knock. When we increase the length scale with suitable level of fluctuation of temperature, we will have super knock. So when we investigate the effect of turbulence, we try to learn from that. We keep the length scale of the temperature here is 5 millimeter, where without turbulence, we will have very strong detonation. We will impose very high turbulence intensity, but with very small length scale. So the idea here is we have very big length scale of temperature. We will stir, we try to use the turbulence to make the eddy size become smaller and smaller. When the eddy size becomes smaller and smaller, the temperature field will be smaller, and it will reduce the detonation developments. Of course, when we consider turbulence, we also need to consider its time scale, how fast the eddy size can move to homogenize the mixture. So here we have a length scale ratio between the ignition delay time with the turbulence ratio versus the time scale of turbulence around 5. It means the turbulence will move 5 times faster than the ignition delay time. So you can see from this animation, for this case, without turbulence, it will feature a very strong detonation. However, when we impose this level of turbulence, you can see the mixture is breakdown. Most of the mixture will be consumed by deflagration. There are some color of alternation, kind of breakdown detonation. Detonation occur locally, and there are no coherent structure. It just locally occur because there are no remaining mixture, and basically most of the mixture is consumed by deflagration. There are some end gas alternation developing into detonation, but not reach the detonation level. because of we impose very high turbulent intensity with small length scale. We also validate with, we also try to run 3D with high turbulent intensity. You can see at early phase, very strong mode of mixture will be consumed by their fluctuation. You can see most of the mixture here is consumed by the their fluctuation, and when it involves, there are some alternation kernel start to establish. Because of turbulence, it will break down the detonation front here. Because it's not detonation front, sorry, it on the way to develop into the detonation, but because of turbulence, it will break down the structure, make the process become slow down. And finally, we can see there are at the end there are some end gas alternation involved into detonation, but it's very weak compared with the case of without turbulence. So here is the comparison between 2D and 3D. You can see here when we impose very high turbulent intensity with small length scale, the structure of the flame is very thin and no collide. Such that even the detonation happen at the end, but it's not like a strong detonation wave. It is low collide event, and because of this one, there are no remaining mixtures to support this detonation front. It will decay at the end, so it's less dangerous than without turbulence. In this study, actually, we use so high temperature, so mixture is so high, so reactive, it can easily go to detonation. However, if we reduce the reactivity of the mixture by decrease the mean temperature, we just decrease the temperature to 1000 Kelvin or 800 Kelvin. Normally, it does in engine condition. There are no detonation development. So reactivity of the mixture is a key parameter. So last question here we learned from previous is length scale is a key parameter. So can turbulence promote the knock intensity? Right now in this case we will change. We will go from very small eddy size of the temperature field, 1 millimeter, small eddy size, and then we increase the turbulent length scale up to 5. So when we increase the turbulent length scale from 1 to 5, the eddy size of turbulence will be bigger and bigger. It will scatter the temperature field to the longer running distance. That may allow for longer running distance for detonation development. So we can see here when we have a high turbulent intensity with big length scale, it can promote knock intensity. You can see this is the case with no turbulent intensity or small length scale. There are no detonation happen here. However, when we have a high turbulent intensity with big length scale, big eddy size, we can promote the detonation development. So the key idea here is mainly is the length scale of the temperature field. It translates to the length scale of the ignition delay field, translate to the C parameter. And if the length scale is long enough to support the detonation running distance, it will favor for detonation development if the mixture is so highly reactive. And the last point here is we try to do the correlation between the FH is the mixture is burned above level of detonation, and the fraction where the mixture is burned beyond the CJ level or ZND level. Let's look at the CJ level here, where the correlation between FH, where the mixture is burned above from DNS, above the this one is from DNS, above the equilibrium one, and here is where the mixture is burned above CJ level. So you can see if the mixture is, the remaining mixture is still abundant, where is an alternation happen, it's very dangerous to bring the mixture to detonation here. However, if the remaining mixture is most of the mixture already unburned, most of the mixture already burned, there are no remaining unburned mixture, we can see that there are no remaining mixture to support detonation. And here is just the case without turbulence and the case with turbulence and the consistent between two. I'm not going into detail here. And I just repeat the key parameter here is when we increase the next scale with a proper level of fluctuation, we can have very high level of detonation, strong detonation. This is for the last part of my presentation is some work in progress we try to publish this year. First one is we apply the machine learning to predict not. So the idea here is for a given initial condition, we can compute the spatial distribution of the C parameter. You can see the C parameter is a ratio between acoustics, the speed of sound versus the speed of the ignition front, where the ignition front can be evaluated according to these equations. So for a given initial condition, we can have initial distribution of the C parameter. And for each different initial condition, we have different field I show here. Some case we have a no knot, my knot, or even super knot. How can we apply machine learning to the initial condition here to train the model? And for any given initial condition, the model can predict whether or not it will go to detonation. And for this prediction, we use a VZZ16 model. It is deep convolutional neural network. This model allows to extract the feature from the image and relate to the event. We characterize the mixture into three different categories: is no knock, my knock, and super knock. And by using all of the initial conditions we have, we change the model and we try to predict. And here is the overall picture. As I mentioned, we try to vary the T prime go from 0.5 to 20, and from the length scale of the eddy size from 1 to above 5, because this is data we have, and the model, the machine learning is provides the prediction quite well. So you can see that. Let's look at this contour for the blue regime here. It's corresponding with no detonation development. So basically, the length scale is about from 1 around approximate about 3. It's consistent with the prediction by the epsilon p. I think this one should be epsilon p. And above this length scale, with certain degree of the fluctuation, you can see the red dot here is corresponding with detonation development. So the prediction by the machine learning with the theoretical framework agree very well. The next part of my presentation is before I just use ethanol. Ethanol is single state ignition. There are no cool flame. So how about the predictions? Can it work with the cool flame like a DME? So when we work with DME, it have a cool flame. What does it mean is when you ignite the mixture, before it reach the main ignition, there are some amount of heat release occur before the main ignition. This is referred to the cool flame. Some amount of so because of this one, heat release, there are some certain increase in the pressure and temperature. Because of the cool flame, the ignition delay is non-monatomic. It will go like this one. In the ethanol case, it just go monatomic like this one. It go up like this one. monotomically. However, for this one, you can see there are some range here. People refer to NTC, negative temperature coefficient. And we try to apply the old model to this DME. However, it is not accurate. We try to compute the critical length scale at which the detonation will develop. The old model is the baseline here, the red curve. The red line here is corresponding with old model. But the old model, it doesn't account for the cool flame, such that you can see it is kind of monatomic behavior. It means that when we increase the temperature, the running distance requirement for each case that decrease monotomically with temperature. So it has the red curve. When I revise this one, I account also for mixture also experience a transient condition. There are some cool flame here before the main ignition, you can see. So we need to account this one. When we account for this one, we can see I revise the criterion and I account it with certain level of fluctuation. I vary here. We will have different critical length scale, but basically when we have cool flame, it will deviate from the old model. So here you can see what I mean here is even at if we pick up the horizontal line here, you can see that at 800 Kelvin, 900 Kelvin something, and 1000 Kelvin something, it has the same critical length scale for detonation development. However, for the old model, the length scale requirement for this case is very long, almost twice. So how can we know old model or new model it work? We try with different initial mean temperature to validate the prediction. And in this DME case, we know that we compute from the new model. We know that the prediction epsilon p equal to 1 when the length scale of the temperature field around 4 millimeter. So here is and here is the result for validation. I mentioned before, for the old model, 810 Kelvin will require very long running distance for detonation development. However, for the new model, we revise, we see that at this level, the mixture start to transit to detonation. This one is epsilon p very close to 1. You can see the ignition process will experience deflagration. Alternation, you can see very strong and gas alternation, and there are some development here. But most of the mixture you can see here is blue one already consumed, so there are no supporting anymore for developing detonation, and it's just decays. Here is just some snapshot. You can see at early phase we have deflagration. There are some alternation take place, and at the end there are some small remaining unburned mixture, and finally we can have some developing detonation. But it is just weakening because there are no remaining unburned mixture to support it, and the overall is the maximum pressure is smaller than CZ level. However, when we keep increasing the length scale up to 5, this case the prediction of is we predict this one is strong detonation. The epsilon p greater than 1, and you can see clearly that after deflagration, alternation deflagration, and yeah, you can see some detonation front start to establish, and it just consumes the rest of the mixture. You can see, and the pressure here is very high. It above the CZ level. So here I just take some snapshot here. You can see I just take the snapshot at the moment where the detonation start to occur, and at the end it just consumes the rest of the mixture by detonation. So it seems that the revised model we're working on is work very well, because at this condition if we use the old model, it will predict that at this condition there are no detonation developed. However, when we account for the cool flame, we observe detonation at this condition. So I forgot to mention about the cool flame here. You can see there are some activity reaction already occur here. That is cool flame. Yeah, this one is cool flame. And after that, there are some hot flame. And because of the cool flame, it makes the mixture already quite reactive, ready for detonation to develop if the mixture is have a big eddy side and suitable then the level of fluctuation. This is the overall picture for the new criterion we have. We go from small eddy side, LT equal to 3, 4, and 5. And as this condition is mainly dominated by strong alternation where the epsilon p is less than 1. So you can see here, when we try to increase the length scale from 3 to 5, by the prediction we have this k is less than 1, this k is approximate 1, and the epsilon p here is greater than 1. You can see in this case, the N-gap alternation can start to developing into detonation, but it does decay very quickly. There are low remaining unburned mixture, so this one is mainly strong alternation dominant. However, when we increase the length scale, where the epsilon p greater than 1, you can see the maximum pressure here is very high, twice greater than this one, and the durations of detonation development here is longer. Here you can see it very short, and here you can see it longer. So it characterizes strong detonation development. We also apply the FD, the fraction where the C parameter ranging from the lower limit, upper limit, and it also predict quite well how many percentage of the mixture is devoted for detonation development. So I am not going into detail. This is only work in progress. I just go through. So the key message I try to deliver here is, without account for the cool flame, the prediction by the old model is inaccurate. When we account for cool flame, the running distance for detonation development much shorter, and this should be taken into account when we compute the critical length scale requirement for detonation development for NTC field like a DME and heptane and hexane. And that's all of my presentation. And here's a key summary. If you look at, if you recall my presentation, so the length scale ratio between the temperature field and the turbulent field is a key parameter. Also is how fast turbulent can mix, is a length ratio between the ignition delay versus the turbulent time scale. They are key parameter. And we also establish the predictive criterions to predict supernova. If it's greater than 1, we will expect that with suitable level of fluctuation, we will have a detonation development. And we also propose the fraction of the FD, the fraction of location where the mode of the mixture is prone to detonation, the C parameter from 1 to 10, it will predict the knock intensity, how many fraction of the mixture will be consumed by detonation. And we also try to apply machine learning to predict supernova, and it give us a good prediction as well. And that's all of my presentation, and thank you very much for your attention.
Yeah, thank you very much, Mingbo. This is very interesting and very informative talk. Yeah, and I have a few questions, but I would like to ask the audience first. Is there any questions or comments? If you do, you can directly unmute yourself and ask Dr. Luong, or you can type your question in chat, then we can read your question. Is there any?
Hi, Minh. Thank you very much for your presentation. I was wondering how important you found the effect of the reflections or interactions between the pressure waves in the forming detonations. So do the detonations just, form regardless of whether there's interactions between the hotspots?
For this study, my boundary condition is periodic. There are no wall boundary. So if you take into account the wall boundary, there is additional effect. I think for 1D model, Zen Chen, he already partially addressed this one, and we also try to account for the wall effect. But in my presentation, there are no wall effects, so I cannot proper answer the question. But there are the effect of wall. But from conclusion from the Zen Chen study, the effect of the wall boundary condition is not first factor contribute to detonation. The first factor is still is C and epsilon parameter.
Thank you. And the interaction between the pressure waves from different hotspots, that's like a secondary factor. Is that what you're saying?
It's just secondary factor. You can see that when the model work very well, it not account for the actual shock interaction. It just account for like you have a lot of eddy size and we decompose into the smallest length scale. And when you have a small, if you have enough running distance, you will have a detonation development. And the mixture should be reactive enough as well. So there are two parameters, the C mean parameter and the epsilon. In this study, I mainly focused on the epsilon parameter because for the C, the mean C parameter is very easy to model. We have one paper for alternation. It already partially addresses one. For the supernova, we can do the similar thing.
Okay, thank you very much.
Yeah, thank you, Minh, for your answer. Is there any other questions, comments from the audience? If not, I would like to ask a question about this two length scales. You have this length scale for temperature, right? Like temperature fluctuation, and the other is the eddy size. I just wonder, like, in the real engine, I'm not really an internal combustion engine expert. My question is, like, what is the condition that give a rise to these two separate length scale? I mean, the eddy size and this temperature fluctuation size. Because what I'm thinking is, like, if you have like very strong turbulence, then the fluctuation or inhomogeneity in temperature is also characterized by the length scale of turbulence or eddies, right? I'm not sure I understand it very well why there are two separate length scales. If there are two separate, that means there are different physical mechanisms give a rise to these two separate length scale, right?
Yeah, I agree with your question. Actually, in experiment, when they measure even for the length scale of temperature or turbulence, it will change in time. Like when you have a compression heating of the piston motion, the length scale will also change. And also, when they design the turbulence, depend on the way they introduce turbulence by tumble or by swirling, the length scale of turbulence will be also can be decoupled with temperature.
Okay.
Slightly, but not significantly. But for theoretical analysis, yeah, we can do it easily because simulation is easy to do. But in experiment, yeah, length scale should be relevant. It cannot be so big difference.
Okay.
Yes.
So is there any correlation between the, for example, the injection or the, the operating dynamics of the engine to the fluctuation or the spatial distribution of this?
I think for like here we have a mode energetic length scale here, LT. It's very close to how big the like when you have intake pipe, how big the pipe is will be, or how big the chamber size is will determine how large the eddy size, the biggest eddy size, and at the end it will transfer to smallest eddy size. And if we have a smaller, very high turbulence intensity, it will determine smallest length scale. It have relevant, I think, yeah.
Okay.
It depend on the actual geometry.
I see.
Even in my symposium paper, we also cite, I think in the FTC paper, yeah, we also refer to some work, even in the engine, when they monitor in different direction, they also can obtain different length scale of the turbulence. But for simulation here, for the like a canonical here, it's very simple. So we just use it kind of isotropic. We look at the smallest length scale we can afford, but in reality, the big length scale is not not account in these simulations. But for detonation, I think it just occur in the smallest length scale, not at bigger length scale, but it will change the flow field.
Okay, I see. This is a very good answer, and thank you for this information. And we have one more question from the audience. It's actually from Professor Wang Han. And I don't know if he wants to unmute himself to ask directly, or he prefer me to just read.
Yeah, I can read his message right now.
Okay. Yeah, I can read for him. It's Hi Minbo. Thank you very much for the impressive work. I'm wondering if we need to consider real gas effects given very high pressure conditions. This is the first question. And the second question is also, knock is low probability events during cycle-to-cycle variations. Is it feasible to predict knock probability via DNS or other methods? Right.
So for the first question, Quang Han, thank Quang Han for the questions. So first question is the real gas effect. I think it is, but we are not in this code we are using. There are we still using the ideal gas equations. There are no real gas equations, so maybe there are some already studies the effect of the real gas. I remember there one study. They conclude the real gas effect, it plays second role, it's not primary role. And regarding his second question regarding to the cycle probability of the detonation, it is because in here for DNS we have one initial condition and we can predict the outcome. However, in the real engines we have cycle variation. It means we have different initial conditions. If we have each different initial condition, we can have a different prediction. And I think this prediction is quite general. If you give me the proper initial field and I can compute it, and it should work. And also for the theoretical analysis, it also suggests at which length scale detonation can occur. So when they design, they will try to avoid this phenomena rather than to prevent circle variation. Or maybe they can use some sensor. They can inject some water or some add more easier to prevent it. But the best case is to avoid it at beginning. I hope I answered Quang Han question.
Yeah, thank you. If Professor Han has a further question, he can leave a message. Is there any other questions or comments? If not, then yeah, I guess I would like to thank Dr. Luong for his impressive presentation today again. Yeah, it's a very good opportunity for us to learn this detonation phenomena occurs in internal combustion engine. For me, at least, it's not a very familiar field for me. So yeah, I really learned a lot from his presentation. And thank you for your time and for all of your participation today. And maybe I will just share my screen to just give an announcement of the next talk. Let me see if
can I stop sharing? Thank you very much.
Yeah, please,
everyone.
Yeah, thank you for your time. Can everybody see my screen? So right now we have a official website, mainly developed by my co-organizer, Dr. Sham Lo Chapdelaine. Yeah, the message, the address of the website is displayed here, and on this website you can. Okay, great. And also you can find all the previous talks, the links to YouTube and the Bilibili channels for season 1, and also the upcoming speakers of the 2nd season. And here we only display for most of the talks, we only display the week of the presentation, and just at least like 1 week before the talk, we will confirm with the speaker of the exact date of the presentation, and we will update it here and also send you the email. For those who want to be added to the mailing list, please let me know. You can email me, and you can also find our contact information on our website. And for the next talk will be next Monday, given by Dr. Josue Maguizo Gavilanes, and the time is slightly different because we want to somehow alternate the time to make it more convenient for our colleagues on the west coast of North America, and also our colleagues in Eastern Asia. So next time it will be slightly earlier than this time, but it's on next Monday. You can find this further information on our website, and also we will send out the announcement email soon. Okay, and thank you all for your participation, and thank you Dr. Mingbo Long today for his interesting presentation.
Yeah, thank you everyone for your time.
Yeah, thank you, and hope to see you all in the future presentations. Bye-bye. Have a good day, have a good night.